week. This week, we need to talk about the relational model, which, as we have said already, is the model of choice for most of the systems that you're going to find out there. So what we're trying to do in this lecture is looking at the theoretical and practical ideas concerned with the relational model, and what you should be able to do at the end of it is identify or define and discuss the relational model of data and understand how relational schemas are constructed. And then in the second part of the lecture, we will go into relational algebra, which is the data manipulation language that we can use within the relational model, and which is quite important because quite often I can ask in the exam questions that might be relational algebra questions. So you need to understand how that works. Equally, obviously, the relational model is hugely important and quite often is something that comes up in an exam. So again, you really need to understand how that works and the fundamental concepts of it. To do this, you need to read Connolly and Beck chapter 4 for this part of the lecture, and there is there additional reading. The code paper is in your reading folder, and you can read it if you like. It's obviously a historical paper from Code who kind of came up with this relational model, and then there is further reading there that you could do. Of course, there are many things that you can read about the relational model. So when we talk about the relational model, the first thing that we need to understand is what is a data model in general. And when we talk about a data model, we're talking about an integrated collection of concepts that describes the data, the relationships between the data, and the constraints of the data. So this is what the relational model needs to provide. When we're talking about in the computer, we are representing real objects. We need to define them by the way of some data models. So what we define about these objects is the objects themselves, but the relationship between them, how they relate to one another, and also what constraints we might put on those objects. And this data model, whatever data model we choose, is going to really give you the concepts and the notations so that you can express the real world in the database, so that the database designers and the end users are going to be able to communicate about the data unambiguously. And that is an important thing, because we need to all understand the database. We all need to understand and communicate about it. So this data model gives us a way of all understanding from a common perspective and communicating about the database. So in order to have a data model, we have to define a number of things. First of all, we need a structural part, and that is going to be the set of rules that allows us to express the objects in the real world in this model. So how the database is going to be constructed in terms of the database world. Then we need to have some integrity rules, which are going to ensure that the data is accurate. And we will see that in the context of the relational model, we are going to have entity integrity and referential integrity as the main integrity rules, and then we might have also domain integrity and some business rules that help us to maintain the integrity of the data. But these are key to the relational model, and you need to understand them well. And then finally, we need to have a set of manipulation rules so we can access and manipulate the data. And that is going to be, in this particular context, relational algebra. And we are going to move to that on the second part of the lecture. So you're going to try to understand relational algebra to understand how you manipulate data with it. And we will explain why learning how to do it with relational algebra is important. Because later on we'll learn how to manipulate data with SQL as well. But the relational algebra aspect is important too. So the theory of the relational model, we discussed it a little bit last week when we were talking about database systems, was mostly developed by a researcher called Code, who in 1970 had this first paper, which was called A Relational Model of Data for Large Shared Data Banks, in which he proposed this type of model. And the idea is that if you use the basis of mathematics and set theory and relational algebra, etc., to manipulate data, you will be able to do it in a more efficient and more consistent way. So he came up with this model, which must have been quite a good model, because up until now, with all of these years of very clever people doing research on all of these subjects, is still the model of choice. So it works quite well. And now we are handling a lot more data than we did in the 60s. and it still works quite well, so it is quite a good model. It has a strong theoretical underpinning, which is based on set theory, and that is what makes it a good model, because we know that mathematical things are described very well. When something is described mathematically, then we quite understand what it says. We understand mathematical notation, and it's very well defined. So that is a very good thing about the relational model. It is based on set theory. So to understand a little bit about the relational model, we need to also understand a little bit about set theory, which hopefully you did when you were in a school. It used to be in Spanish schools the first thing that you learn in maths, with Venn diagrams and apples and pears. Did you do that in school? Does it work like that in England? You do, well, or wherever you come from. You do set theory with apples and pears and sets. So you have to refresh your memory to all of this. And the idea is that when we have a set, all of the members of the set are of the same type. So if I have defined a set of apples, everything in the set must be a set of an apple. If I define a set of pears, everything in the set has to be a pear. If I design a set of fruits, I could have pears and apples, but then I'll define it differently. But everything in my set has to be of the same type. So that is one important thing in set theory, also an important thing in the context of the relational model. Another thing is that, and this is very important to both set theory and the relational model, is that you can only have one instance of a particular object in the set. So I might have many apples, but each is an individual apple. There is not another copy of the same apple. They're all individual objects in a set. And this is important also to the relational model. Every data item has to be individual and unique, and uniquely identifiable. So this is an important property of sets that matter to the relational model. And the other thing that matters is that the sequence of items, how you order them, is unimportant in terms of set theory. So it doesn't matter whether you have this pair before this pair or this student before this student. It is all the same. It's the same set however you arrange them. You might arrange them in a particular order because you want to, but it's not going to make a difference to the set. Let me close the door. Because I am a loud person, which I have to be in order to reach you all, but I'm sure that everybody doesn't want to know my lecture. So, once we have all of those properties, what we also know is that we can define subsets over sets. So if I have the set of fruit, the set of apples might be a subset of the set of fruits, and the set of bananas might be a subset of the set of fruits. If I have the set of students, the undergraduates might be a subset, and the postgraduates might be another subset. And I can go on defining subsets as long as I define them by some property. And once I have sets, I can also define operations on those sets. And the operations you should remember from your school days are the union of two sets, the intersection of two sets, and set difference, at least those. You should remember those. If you don't, they will come along today, and you will remember them. So these are kind of like the operations that we are going to define on sets. So why do we actually have this relational model? Well, first of all, what we want to attain with this relational model is this independence. We talked about it in the last lecture. We said what we want to do is separate the data implementation from the data definition. We want to be able to change the data definition, where the data is stored, without affecting all of the users. So this is providing independence. So this relational model is thought out with this concept in mind. It's supposed to allow you this independence that we seek in the data. And also it's going to allow us to deal with things like data semantics, consistency, and redundancy problems. So we're going to try to avoid things like repetition in the data. Now, Code continued to investigate and came up with this concept of normalization, which we will have a lecture on, and it's looking at repeating groups and how you avoid repeated data in a database, or how you control redundancy. So that is also important to the relational model. And it's also going to allow us to expand set-oriented data manipulation languages such as relational algebra, SQL, which is now the manipulation language of choice, is an expansion of the concepts in relational algebra, relational calculus, etc. So by having this model, we can do all of these things. We provide the language that we can interact with the data. We provide these very good normalized relations which avoid repetition. And we can also give data independence, which are three good things that we didn't have before. So if we go back to the last lecture, which some of you did remember, when we talked about this three-level ANSYS Spark architecture, we have our external level, which could be a number of views for different sets of users. We have our conceptual level, which was the whole entire data model, the whole database. And then we had the internal level, which was how we were actually going to implement that physically, storage, indexes, etc. So the relational model is going to help us to express the conceptual level. So it's going to allow us to define the data in the database, all of the data. From that, we will define the views. And from that, we'll be able to then go on and decide how we're going to store that data. But we don't have to worry in the relational model about how we store the data or how we access the data, because we're separating the data kind of like a structure from the data definition in a way. So if we think about earlier models, like the hierarchical model or the network model, you needed to understand the structure of the data, because it was a set of pointers, and it was either a hierarchical set of pointers or a network set of pointers in order to manipulate the data. This relational model is going to remove that need. So we're going to be able to manipulate the data without having to worry about how the data is stored and what data structure underlies the data. So there we get data independence. So are we all happy so far with all of that? Understanding? Yes? Okay. So the very good thing about the relational model is very simple to understand. It holds all the data, including the metadata, in tables. So as long as you understand the structure of the table, you are going to understand the data structures. Because all we have in the relational model is tables. And tables are composed of columns, which represent attributes or fields, and records, or rows, or tuples, which contain the individual objects in the database. So a database is going to be a set of related tables, interrelated tables in some way. That is going to be our data model, our relational data. So it's going to be a set of interrelated tables. This is good because it's very simple and intuitive. You can understand it. We are going to be able to implement the conceptual schema using this set of tables and nothing else. From that, we can derive external schemas to suit different users and their needs, and it places no restrictions on how we implement this, how we store the tables in physical memory. Doesn't matter to us, because the conceptual model is only going to see the data as a set of tables, regardless of how we then store them for later access. So some terminology that we need to understand in the context of a relational model is things like a relation. A relation and a table are the same thing. Relation is a mathematical term because it's derived from relations, as we will see in mathematics. Table is a term that you might more often understand. And within this, we have the base relations or base tables that we define, and we have views, which are derived from the base relations, and might or might not be stored physically in main memory. Views are not necessarily always stored. Sometimes they are computed at the time that we require them. So because of that, they are virtual relations. We also have attributes, which are named columns. So if I have a student, the student number, the student name, the student address will all be attributes of my table. And they hold data about individual objects, in this case, individual students. And they can appear in any order in the relation, because we said order is immaterial to sets, is immaterial to relations, and is immaterial to the relational model. In effect, we often want them in a particular order or display them in a particular order. But if we change that order, the relation is the same. It doesn't matter to us what order the attributes appear in. Then we have domains. Domains are an important concept derived from mathematics. If I have anything like age, the domain is the range of allowable values. So for age, what is the range of allowable values? Well, for age of a person, it's probably from 0 to something like 120 or 130. If I look at the age of a tortoise, maybe it'll be from 0 to 500. If I think about something like temperature, in Britain, it might be -10 to 30 in a lucky day. If I look at the temperature in other places, it will change. So it's a set of allowable values. Some domains are easy to define, for example, age or temperature. Some domains are very difficult to define, for example, surname, because anything could be a surname, particularly if you look internationally. So some domains are finite, some domains undefinable, some domains are infinite, and you can't define them. Other things that we have is a tuple. A tuple is the same as a row or a record. So it's one instance, one object represented in the database with values for the particular attributes. And as we said, for sets, every object is unique. And for relations, the same applies. Every tuple must be unique in a relation. You cannot have tuples that are duplicated. So that's an important property of a relation. They must be unique and uniquely identifiable. Other terminology you might come across are things like the degree, which might be the number of attributes in a relation, and the cardinality, which might be the number of tuples or records in the relation. And when we go to ER diagrams, cardinality and degree will have a different meaning. In this context, this is what they mean. So if we look at the terminology, there you have how the terminology relates. So a relation, a table, and a file are more or less the same thing. A file will probably be the parlance of the old file-based systems, whereas in the modern relational model, we talk about either relations or tables. They are the same. A tuple is a more mathematical name. A row is the same, or a record in the old kind of like way of looking at things. And you also have attributes or columns, whatever, the same, or fields in the old terminology. So those are the things that you will hear of again and again in the relational model. So going back to how the relational model was created, you remember that last week we already talked about the fact that all of this need to store data more efficiently came about around the 1970s, when they were starting to come up with projects that could generate a lot of data, like the moon landing project and others. So they had a need to have better ways of storing and analyzing data, and therefore Code in the 1970s started to research this, talk about the relational model of data, wrote a paper on it, and this quickly caught on because it was a good model. And you find that other people like Date worked on it. He wrote a book which has been quite influential in database systems. And Code later on worked on things like normalization, which was actually making relations better in terms of defining very desirable properties of a relation. And all of these kind of started to transpire into research systems in the 1970s. These research systems were made to show that the relational model was a good model and that it could be implemented. So there were things like System R from IBM, SQL and DB2 started to come up just to prove that these concepts in the relational model were powerful concepts for storing data and accessing data. There were others like Stonebreaker, Ingress, Postgres, which we are going to use, etc. That then kind of like became mainstream around the 80s, where commercial packages appeared that follow this relational model, like Oracle, IBM DB2, Infomix, Sybase, SQL Server. They all began to implement this relational model because this became the model of choice for databases. And in the 90s, they appeared in desktops, things like Paradox, MS Access, etc. So they kind of like became even more mainstream. Now, around the 90s as well, when there was a lot of activity around object orientation, there was some movement to object orientation in terms of databases, but purely object-oriented databases did not catch on properly. So most of the databases that you find out there are relational model databases which might have extended capabilities, which can deal with object orientation. But generally speaking, the model of choice is still the relational model. So if we think of an example that we will use through the lecture as we go ahead, because it's a simple example, but good enough for most of our purposes, we might have three relations there. One of them lists suppliers for a particular thing. They could be bicycles or anything else you wish to care about. And what we have is that we have a table which is going to implement the object supplier. And it's going to have a supplier number, a supplier name, a status, and a city where the supplier is located. And then we might have another table for the shipments. And that is going to have the supplier number, the part number that has been shipped, and the quantity. And then we might have another table, which is the parts table, which has a part number, a name, a color, the weight of the part, and the city where it's being shipped to, or where the part is required. So if we have those three tables, they might constitute a relational database, because we have three different objects which are represented in the relational model. There are some relations between them, which we will see. Suppliers supply parts in shipments, so there is relationships between the suppliers, the shipments, and the parts, and there might be some constraints on how we use that data. And the schemas are defined there. The name of the table is before the bracket, S, SP, and P, and inside of the bracket we have all the different attributes or columns that form that particular schema, and then we can see examples of the objects there for that particular schema. So the notation that we're using there for the schema is in front of the bracket we put the schema name, the relation name, and then inside the bracket we have the attributes, and we've underlined the primary key. And we will see that the primary key is going to become a very important concept in terms of databases and the relational model. So that is a schema for a particular database. It's a description of the database. So if we go back to the mathematical basis of relations, let's see how relations appear in the mathematical world, or in the world of set theory and so on. So if we have two sets, D1 and D2, and each set has a domain of values that is allowed for that particular set, then D1 has objects 2 and 4, and D2 has objects 1, 3, and 5. If I want to define the Cartesian product, which is a set operation, of D1 and D2, that is defined as the set of all ordered pairs, where the first element is taken from the first set, D1, and the second element is taken from the second set, D2. So the Cartesian product of D1 and D2 is going to be made up of 2 and 1, and 2 and 3, and 2 and 5, because I'm taking an element from the first set, and an element from the second set, and then 4 and 1, 4 and 3, 4 and 5. So all of those together are the Cartesian set, the Cartesian product of set D1 and D2. If I now define any subset of the Cartesian product, that is a relation, and that's where the name relation comes from. So if I now say, for example, I want a relation that is formed of all the pairs x and y, such that x belongs to the first set, y belongs to the second set, and y is equal to 1. That is a relation. It's a subset of the Cartesian product, and is defined by all of the elements, paired elements, where the second element is 1. So that is going to be 2, 1, and 4, 1. So it's a subset of the Cartesian product. I could define another one. We said the second set is, the second element is less than the first element. I can define any kind of relation as I like. They will all be relations of the Cartesian product. So we can generalize this also to any n domains. We don't have to do it for 2 domains. We could have the Cartesian product of D1 times D2 times D3, and then I could set relations by defining properties that the objects have to meet to be part of the relation. So I can specify any Cartesian products of any number of sets, and then I can have relations defined on that Cartesian product. So why does that matter in terms of the relational model? Well, there are a number of properties of a relation in maths that are important to the relational model. The first one is that the relation name is distinct from all other relations. So in the context of a database, a relation or a table has to have a distinct name. All of the relations may have their own distinct name. Each cell of the relation must contain exactly one value at the intersection of a row and a column. And that's again very important to the relational model. There cannot be any repeating groups or complex entries. So for example, if I stored sports and I put judo, football, and tennis, that will break the relational model, because at the intersection of a column and a row, I can only have one single value. So if I have three values stored in the same cell, that will not be in conformance to the relational model. It will be different if I interpret it as a test string, and I just say rugby, football, etc. is one test string. Okay, but if I am identifying them as individual sports played, then I cannot have three stored under the same cell. Each attribute in a relation also has to have a distinct name. We could have attributes in different relations having the same name. But because the relation has a distinct name, they will still be uniquely identifiable, because I will say relation name dot attribute. Even if there is another attribute of the same name, in the contents of the relational model, I can qualify it with the relation name, and it becomes unique. And remember that order has no significance, so the order of the attributes doesn't matter. The order of the tuples in the relation does not matter. It doesn't change the relation. And very importantly, each tuple is unique and must be uniquely identifiable. And as I say, the order of the tuples has no significance, even if we want to order them in a particular way. So we might want to order the students in a student number order, but it doesn't alter the relation. That is how we wish to see the data. It doesn't change the relation that is holding the data. Everybody's happy with this? Or do you have any questions on this? All happy? You understand what I said? Good, good. So some of these things, again, could be an exam question. So I could say to you, what are the mathematical properties of a relation that are important in the context of the relational model? In which case, I'll expect you to discuss those things. Okay? So it's important that you understand it. Now we move to a part which is important to understand as well in the relational model, and this is the concept of keys. Candidate keys, super keys, and primary keys. So if we think about the super key, that is any attribute or a set of attributes. It doesn't have to be an individual attribute, it could be composite, which uniquely identifies a tuple. So anything that uniquely identifies a tuple is going to be a super key. For example, the national insurance number for a person uniquely identifies that person, because no two people should have the same, so that is a super key. I could also have the postcode and the house name number. That uniquely identifies not necessarily a person, but a family. Okay, so if I wanted to store perhaps something to do with the postcode, that would be fine. If I wanted to identify uniquely individuals, I might need some of the detail like the surname to make it unique. Or even the first name and surname, if the two people that live there are married, because they will share the same surname. When we think about the super key, in it you might have attributes that do not count to uniqueness. So for example, if I have national insurance number and surname as a super key, surname there is not necessary because it doesn't count to uniqueness. National insurance number alone is unique. So that is a super key, but it's not a candidate key. A candidate key is one in which all of the elements are necessary for that candidate key to be unique. So no proper subset is also a super key. Then you have a candidate key. Okay? So for example, national insurance is a candidate key because it uniquely identifies a tuple, and there is nothing in it that you could remove without it being not unique anymore. But national insurance and surname might not be a good candidate key, because you don't need surname to make something unique. Postcode and house number may be a candidate key, because you might need those two things to identify the tuple uniquely. So, candidate keys are any irreducible combination of attributes that we have. And from those candidate keys, we are going to choose one to be the primary key. And this is what is going to uniquely identify each tuple in the database. So it's very important. Every relation must have a primary key. And the primary key is going to have the two properties of uniqueness, because it uniquely identifies the tuple, but also irreducibility. You cannot get rid of any of the attributes without losing the uniqueness property. So, for example, NI and surname is not irreducible, because I could get rid of surname, so it's not a candidate key, and it won't be a primary key. So once we've defined the candidate keys, we need to choose one which is going to be the primary key for the table. And it's going to be whatever we choose to identify uniquely the tuples. There is going to be always one per relation. And in the worst case, if we put all of the attributes together, that should be unique. Mind you, to be a primary key, it will have to be irreducible. So it will have to be, there are cases where you need all of the attributes to make something unique. In the worst case, this could be it. It wouldn't be a very good primary key, because it will be very long to query without primary key, but it's a possibility. The candidate keys that you do not choose to be the primary key are sometimes called the alternate keys, or the surrogate keys. So they are the candidate keys that you're not using as a primary key. Now, the other very important thing, because it makes the whole of the relational model link, and it allows you to establish the relationship between objects, here is the foreign key. A foreign key is an attribute or a set of attributes, because it can be composite, which matches a candidate key of some other relation. So I have my primary key and I have a foreign key. And the foreign key will match the primary key in another table, or sometimes even in the same table. The foreign key acts as a reference to another table. It helps you to link two tables together. So for example, it's a lookup. So for example, if I have a branch number, I have this table where I have a staff, and I have a staff number which I have identified to be the primary key. I've underlined it. And I have name, salary, and branch number, manager number. Here both branch number and manager number are acting as foreign keys. They are acting as a link to a table. In the case of branch manager, branch number is going to be a link to the branch table. So what that enables me to do is, if I have an object which is a staff member, and I have an object which is a branch, I can put together the information on the staff and the branch, because I can link those tables together. So it allows me to implement relationships between objects. The manager number in this case, which is also a foreign key, is linking to the same table. So it's saying, it's allowing me to, for any staff, identify who is the manager. And if I have the manager, I'll be able to identify who he manages. So it's acting as a link to the same table. So it's a mechanism for implementing the relationships in the tables. So generally, a foreign key links to a primary key in another table, but it could also link to a candidate key in another table. It doesn't have to link always to a primary key. It could link to a candidate key. Are we all happy with this? Because this is pretty important. If you don't understand that,
yes, if you want to make a primary key, can we just make integer ID, or it's better to choose?
You normally do. So most often you will create a unique key, which might be an integer, or it might be a sequence of characters, which will be unique. And that will be your identifier. But there might be cases where you don't do that, where you have a linked table which will actually use a set of combined attributes as a primary key, instead of being identified uniquely. And we will see instances where that maybe make more sense. where we have intersection tables. So the idea here is that we have something like this, okay? So let's say that I have a staff table and I have a branch table. And I have my branches here, B5, B7, B3, B4, B2, with the street, the city, and the postcode. So this is my cardinality, these are my attributes, this is one relation, and this is another. Now here I have the staff table, which has a staff number, F name, last name, position, sex, date of birth, salary, and branch number. Now if I wanted to know, for example, the details of John White, or White, I go and I say, okay, his branch is B005, so I can link to this table and find all of the details of the branch he works in. Equally, the other way, if I wanted to work out who works in branch 3, I could look here and find all of those that work in branch 3 and get all the details. So it allows me to link information from one table to another. And it's always a one-to-many link. Generally speaking, we have here one tuple, so we have many staff which link to one branch. One staff, one branch links to many tuples. Okay? So the links are always one to many. And we can then put information together. So there is my foreign key, which references my primary key. And that is a relationship between the two tables. Are we all happy with that? Fabulous. So if I now ask you, in that, I have a viewing of a house. So I have a set of customers that go to view houses that they want to buy. And I'm storing that in some relation, which is called viewing, and I will store the client number, the property number, the view date, and the comment. What is a sensible primary key for that table? Or what is a candidate key for that table? Client number. Okay, so I have a list of viewings. Is client number going to be unique?
Yes.
So the client is only ever going to appear once in the viewing table. What if you view more than one house? Is he unique then? So is that a primary key? No, because it doesn't identify uniquely an object unless you assume that a client can only ever view one house, which is not likely to be the case.
What happens if you use a composite key for client number and property number?
Okay, so you have now client number and property number. Is that going to be unique? No, because?
View two houses on the same time.
Exactly. What happens if you wanted to view two houses? Indeed, if you go to view the same house twice, because normally when you buy a house, you go, you view it once, then you take your auntie and your children and you view it again, then you take your husband again and you view it again, and eventually you buy it. So is it going to be unique? No. So what do we need? Client number, property number, and lease and view date. Because that allows us to have the client visiting the same property more than once. Are they going to view it more than once per day? If they are, then we also need no, we don't have I thought we might have a time, but we don't. If we had a time, then we might need that, okay? If we don't have the time, then we're assuming that they're not going to view it more than once per day, because otherwise our table will be screwed, because it would not be unique tuples. What about if I have an assignment? So I have people that are assigned to particular projects. So I have a project number, an engineering surname, engineer first name, and assignment date. So we have people being assigned to, engineers being assigned to different projects. What do I need there as a key? Anyone? Ask us, I guess. So I have project numbers, engineer surname, engineer first name, and assignment date.
That's three.
The first three at least, yeah. If I have project number alone, if I assign that project to more than one engineer, that is not unique. If I have project number and engineer surname, if I have two engineers of the same surname, which in a good company, the Smith will happen twice, then it's not unique. So I might also need engineer first name, and if this engineer is assigned and deassigned and assigned again, then again he might appear more than once, so I might also need the assignment date, if they can go in and out of the assignment. So you've got to think, when you think about the primary key, of this issue of uniqueness. On one hand, the key has to be reducible, so you don't want to have anything on it that is not necessary for uniqueness. But on the other hand, you need to think of the whole context of the enterprise and what is going to be unique in that context. Same if I have a hotel. So I make a booking as a customer in hotel.com. I'm going for a holiday. So I have my hotel number, the guest number, missing a T, the date from, the date to, and the room number. So what is a unique key in that context? Guest number and date to. So what is the same case? Well, geez, yeah, that might work because it's unlikely to book more than one room in the same date. So that might work as a key. Because normally you cannot be in twice, unless you're booking on your name for different people, in which case, potentially, you could have the same guy appearing in one hotel here, and then he books his cousin in another hotel under the name. If that's the scenario, then you might need to have also the hotel number in there. So you've got to think about it in context and think what is the right key to have in that context. Obviously, you need to understand your data quite well in order to do that. So are we all happy that we understand this concept of a primary key? Good, because that is an important part of it. So the next thing that we need to understand is null values. Null values appear in databases, and this is where we don't have a value, we have a blank, something didn't enter, wasn't entered. Now, either the data is not available or it doesn't fit the particular purpose, but it's still, we have to enter it. So if we have something like that, we have to be aware that it makes life very difficult. We will see how it complicates queries, but because missing data is a real life issue, it will appear in databases. But whenever we have null values, databases are complicated and queries are complicated. And null values is not a zero, it's the lack of a value. So it doesn't equate to a zero and it doesn't equate to an empty string. It's just where you don't have a value at all. Okay, so that is a null value. They are controversial in relational systems, they are controversial in computing in general, because dealing with missing data is quite a difficult thing to do. But it is there, and we have to represent it and deal with it. So, we said that when we talk about the relational model, there are three things that we have to understand. The first thing is the structural part, and we've already talked about that. We've defined the tables, we've defined the primary keys of the tables, we've defined that everything is a table. We've talked about columns or attributes and records, so we begin to have an understanding of the structural part. The other thing that we said was important to a data model was the integrity constraints. And this is what allows us to keep the data in the model of good quality. In the case of the relational model, there are three main constraints that you need to understand, two of which are very important, and the domain integrity is also important, but sometimes more difficult to implement. The first one is entity integrity, and that simply says that no attribute of a primary key can be null, ever. Okay? So anything that participates, any attribute that participates in a primary key cannot have null values, by definition. Because if they do have null values, then they wouldn't be necessary for the key. So you will break the irreducibility principle. So entity integrity just tells you that if you have a primary key, any attribute that forms part of the primary key cannot be null. Okay? Simple enough and hopefully easy to remember. Domain integrity is to do with placing constraints on the values of attributes. Now, depending on the domain, this is easy or difficult. So sometimes we can implement domain constraints. So for example, if we have age, we can quickly constrain age because we want an integer, and it has to be between 0 and, let's say, for a person, 120 or 130, wherever we think is the longest somebody can live. Sex is also very easy to have a domain constraint on because it can only be male or female, so that is fair enough. We can sometimes use defaults to define a particular domain. So for example, for students, we could say if we don't know what they are, we define undergraduate to be the default. But some domains may not be so easy to define. All we can define is the data type. So for example, for surname, all we can define is it's going to be a string of characters. But a Chinese surname might be completely different to a British surname or a Spanish surname. In fact, if you go to Spanish surnames, we have two instead of one. so it becomes quite difficult to define domains in some contexts, whereas in others it is more simple to define. Now, the second most important constraint after entity integrity is what we call referential integrity. And that is what enables us to keep the data model whole. So that tells you that if a foreign key exists, it must match an existing candidate key or be wholly null. So if I have an employee who is assigned to a branch, it either has to be assigned to an existing branch or be wholly null. I cannot have a reference to a branch that does not exist anymore, because that will break the integrity of the model. Okay? So, in that context, if I have a shipment, the reference to the part that is being shipped and the reference to the supplier that is supplying the part has to be a reference that exists both in the supplier table and in the parts table. Or, alternatively, if we allow nulls for that value, it has to be wholly null. So the only other option would be that both the supplier table, the supplier reference, and the parts reference were both null in that particular table. Now, when this causes a problem is when you insert, update, or delete data. So let's say that I have a branch, and I have a set of staff that are allocated to that particular branch. If I want to delete that branch, what do I do with all the staff that is assigned to that particular branch? If I allow the deletion without any further ado, let's say that I allow the deletion and 10 employees were assigned to branch 3, I delete branch 3, the references in the employee table will be invalid because they reference something that does no longer exist. So I've broken referential integrity. I've broken the model, and that is not allowed. So I have a number of choices. What I can do is either restrict the deletion, and that means that when I set up the table, I say I'm going to restrict the deletion, and this is the default choice if you don't say what's going to happen. So I will not allow, the system will allow me to delete the branch if that branch has associated staff. The deletion will be will return an error, and it will say you cannot delete because of referential integrity constraint. Another action that I could take is I cascade the deletion. So I delete all of the employees associated with that branch. Obviously, that is not an action that you want to take lightly because you could delete accidentally a lot of data that you didn't mean to delete. So you will only cascade the deletion in cases where you're very clear that this is the right action to take. And we will look at that in the seminars. And alternatively, if I have a default branch, I could say, okay, set the branch when I delete in the staff to the default branch, whatever that might be, maybe the London branch. Or I could set to null if the branch number in the employee table allows null. So those are the 4 actions that I can take. Either I restrict the deletion, I cascade the deletion, I set the branch in the employee record to be the default branch, or I set it to null if it allows nulls. Okay, and I make these decisions when I'm setting up my tables, because this is how I enforce referential integrity. And all that referential integrity is telling me is that if there is a reference, it has to be a valid reference, or it has to be wholly null. Okay? Are we all happy with that? Do we understand referential integrity? Yes. No. If not, ask now. Or later, it will be too late. So this is a problem for you before we have a break. What is wrong with those relations? So the first one, is that an okay relation or not? No, because? Exactly. There is a tuple that is repeated there. There is an S1P1 300. So the tuples are not unique. So that cannot be a relation, because we don't have uniqueness of tuples. Therefore, that is incorrect. What about the second one? Do we have anything in the parts table that might be wrong? Three colors. This is not allowed because we know that at the intersection of a row and a column we can only have one value. So if we have 3 values, that does not comply with the relational model and is therefore not a valid relation. So 3 colors is a problem. Anything else?
If
Heavy, indeed. Every value must be drawn from the same domain. So if the domain is the domain of integers or real numbers, 12 and 17 belong to that domain, but heavy does not. So that is, again, breaking domain integrity. Anything else? Yeah, one of the columns doesn't have a name, so it's not uniquely identifiable. Again, that is not allowed in the relational model because we said every column has to be uniquely identifiable. So there's a number of reasons there where that is not complying with the relational model. Okay, let's have a break.